Watch liquid steel pour from a ladle, glowing white at 3,000 degrees, bright enough to burn your retinas instantly. 20 tons cascading like luminous waterfall into molds, each splash throwing sparks 50 feet. This isn't new steel from ore, it's recycled. Yesterday's junked cars, demolished buildings, scrapped appliances melted and reborn. America recycles 80 million tons of steel annually, more than all other materials combined. That rebar in your building's foundation? Average age: 73 years through 4 previous lives. How does rusted scrap transform into structural steel stronger than original? Why does recycled steel outperform virgin steel in crucial applications? Stay with us. You'll witness industrial-scale alchemy turning garbage into skyscrapers and discover steel's shocking secret. It's infinitely recyclable without quality loss, forever. Nucor Steel's Berkeley facility in South Carolina processes 3 million tons annually, enough steel to build 15 Golden Gate bridges yearly. The scrapyard stretches half a mile, mountains of metal sorted by type. Shredded cars pile 6 stories high. Railroad rails stack like pickup sticks. Crushed appliances form metal glaciers. Giant cranes with electromagnets strong enough to lift entire automobiles move continuously, sorting, stacking, organizing chaos. Watch the shredder operation. A hammer mill the size of 2-story house contains rotating drum with 50 hammers, each weighing 300 pounds. Cars feed in whole, no disassembly required. In 8 seconds, automobile becomes fist-sized chunks. The noise defies description, continuous thunder as metal destroys metal. The shredder processes 100 cars hourly, 6,000 monthly. Every junked vehicle in America eventually passes through facilities like this. Nothing wastes. Even copper wiring gets separated and recycled independently. The electric arc furnace, EAF, is where steel is reborn. This vessel, 40 feet diameter and 30 feet deep, operates through electrical violence. 3 graphite electrodes, each 2 feet thick and 15 feet long, descend from the roof. When power flows, 90 megawatts, enough electricity for 70,000 homes, arcs jump between electrodes and scrap, generating temperatures exceeding 5,000 degrees. The initial charge contains 200 tons of scrap steel loaded via overhead buckets. Operators lower electrodes carefully. Too fast, they shatter. Too slow, productivity suffers. The arc strikes with deafening crack. Visible through protective glass is blinding white plasma. Metal begins melting immediately. The sound evolves from cracking to roaring as molten pool forms. Watching through infrared cameras reveals the chaos. Solid metal liquefying, impurities rising as slag. The melt cycle takes 45 minutes start to finish. Chemistry happens through violence and precision simultaneously. Oxygen lances inject pure oxygen into molten steel at supersonic speeds. The oxygen burns impurities, carbon, sulfur, phosphorus, creating slag that floats atop the denser steel. Temperature reaches 5,800 degrees at plasma core, hot enough to vaporize iron itself. Cooling water circulates through furnace walls at 5,000 gallons per minute, preventing meltdown. Alloying additions fine-tune steel composition. Computer-controlled systems add precise amounts of manganese, chromium, nickel, elements determining final properties. High-strength rebar requires different chemistry than structural beams. The metallurgist's console displays real-time analysis via spectrometer. Laser vaporizes steel sample. Computer analyzes emitted light, identifying every element present to parts per million accuracy. Adjustments happen in real time. Chemistry perfected before tapping begins. Tapping releases the dragon. The furnace tilts hydraulically, massive vessel rotating on trunnions. Molten steel pours through tap hole into waiting ladle, refractory lined bucket containing 40 tons of liquid metal. The pour takes 6 minutes, continuous stream of glowing steel creating updrafts so powerful, they lift dust and debris into the air. The temperature, 3,050 degrees, radiates heat felt 200 feet away. The ladle, mounted on railcar, travels to continuous caster. This machine revolutionized steelmaking, replacing individual mold casting with endless process. Molten steel flows from ladle into tundish, then into water-cooled copper molds oscillating up and down. As steel contacts mold, outer shell solidifies while interior remains molten. The strand, continuous ribbon of steel 8 inches square, emerges from bottom at controlled speed, bent gradually from vertical to horizontal through roller system. The hot rolling mill is where shape is born. The continuous cast billet, still glowing red at 2000 degrees, enters the roughing mill. Giant rollers, each weighing 30 tons, squeeze the steel, reducing thickness while increasing length. The transformation is violent. 8-inch square becomes flat bar 6 feet wide and quarter-inch thick in 7 passes through successive roller stands. Watch the mill operation. The steel screams through at 40 miles per hour, extending like taffy as rollers compress it. Water jets cool rollers constantly. Without cooling, the steel would weld itself to roller surfaces. Scale. Iron oxide forming on surface gets blasted away by high-pressure water, creating permanent rainbow mist in the mill. The noise is beyond hearing protection. Low-frequency vibration felt in bones. One operator describes it. Steel doesn't want to be flat. We convince it otherwise through controlled violence. Cooling determines final properties through metallurgical magic. After final rolling pass, steel enters cooling bed, where water jets precisely control cooling rate. Fast cooling creates hard, brittle steel. Slow cooling produces soft, ductile steel. Controlled cooling, varying rates across thickness, creates exactly desired microstructure. Computer systems adjust water flow based on steel grade, thickness, ambient temperature. The coiler winds finished steel into massive coils, 40 inches wide, 1 mile long, weighing 25 tons. These coils ship to manufacturers producing everything from automobiles to appliances. Some steel goes to galvanizing lines where molten zinc coating prevents rust. Other steel gets further processed, cold rolled for precision applications, annealed for formability. But the core material, recycled steel, remains unchanged, ready for another century of service. Steel recycling accelerated during World War II when scrap drives collected every available piece of metal for weapons production. Post-war, technological advances made recycling economically viable. The electric arc furnace, developed in 1960s, eliminated need for iron ore. Recycling became primary production method. By 1980s, mini-mills using EAF technology revolutionized the industry, undercutting integrated mills using blast furnaces. Today, America produces 70% of steel from recycled scrap. Traditional integrated mills using iron ore and blast furnaces still exist but increasingly rely on scrap supplementation. The transition reflects economic and environmental reality. Recycling uses 60% less energy than primary production. A single steel mill prevents mining hundreds of thousands of tons of iron ore annually. The industry transformed from extraction to circulation, steel cycling endlessly through economy. Carbon emissions dropped 65% using recycled steel versus virgin production. Industry saves $58 billion annually avoiding ore mining and processing. Each recycled ton prevents 4 tons of raw material extraction. Ore, coal, limestone combined. Here's the secret we promised. Steel is infinitely recyclable without degradation. Unlike plastic degrading with each recycle, steel maintains properties indefinitely. That nail holding your wall could have been Roman sword, railroad spike, Model T chassis, World War II tank, 1960s Cadillac, demolished skyscraper, and now construction steel. Same iron atom serving humanity for millennia. The crystal structure reforms perfectly during melting, erasing all history. Impurities burn away in the furnace, chemistry optimized through modern metallurgy. From junkyard to job site, the transformation completes. We've created closed-loop system where waste becomes resource, garbage becomes infrastructure. That bridge you drove across, those rails carrying freight, the frame supporting your office, all contain steel recycled dozens of times. The metal never tires, never weakens, never remembers its past. We've mastered material that improves through use, strengthened by human engineering beyond nature's intention. Steel isn't consumed. It circulates, eternally useful, permanently valuable, waiting only to be reshaped for next purpose. Civilization built on metal that refuses to die. Hold a 1-inch tungsten cube. It weighs nearly 1 pound, denser than gold, heavier than lead. Drop it and the floor dents, not the cube. This metal refuses to melt until 6,192 degrees, hotter than Earth's core beyond temperature where other metals vaporize. Light bulb filaments, armor-piercing bullets, rocket nozzles. Tungsten survives conditions that destroy everything else. Yet it starts as dull gray rock, looking worthless. How does brittle ore transform into metal that won't surrender? Why does one nation control 70% of global supply? Stay with us. You'll witness industrial-scale mining reshaping mountains and discover tungsten's shocking secret. This indestructible metal is so brittle in pure form it shatters like glass. The Dayu tungsten mine in Jiangxi, China dominates the landscape. An open pit 3 miles across descending 800 feet into earth. Giant haul trucks, each carrying 400 tons, crawl spiral roads looking like toys from rim's edge. This single mine produces 40,000 tons of tungsten concentrate annually, enough to manufacture 2 billion light bulbs. 70% of world's tungsten comes from Chinese operations like this. Watch the blast sequence. Drillers bore holes 50 feet deep in geometric patterns across the pit floor. Each hole gets packed with explosives, 200 pounds per hole, hundreds of holes per blast. The detonation ripples across the face in sequence, fracturing 10,000 tons of rock in 30 seconds. Dust clouds billow 300 feet high, visible from orbit. What took nature millions of years to create, humans demolish in half a minute. The ore, wolframite and scheelite, contains just 0.5% tungsten. That means 99.5% is waste requiring removal. Massive crushers reduce boulders to gravel. Ball mills grind further. Rotating drums containing steel balls pulverize ore to powder finer than flour. The grinding noise is deafening, continuous thunder as metal crushes rock. Separation uses gravity and magnetism. Wolframite, being dense and magnetic, concentrates easily. Scheelite requires froth flotation. Chemicals make tungsten minerals hydrophobic, clinging to bubbles while waste sinks. The concentrate, now 15% tungsten, ships to processing plants. China's dominance isn't accidental. They control reserves, processing knowledge, and critically tolerate environmental damage Western nations won't accept. Tailings ponds stretch miles, filled with chemical-laced sludge that'll remain toxic for centuries. Processing concentrate into pure tungsten trioxide requires acid digestion. The concentrate gets dissolved in hydrochloric or nitric acid, violent chemical attack breaking molecular bonds. Tungsten dissolves while impurities precipitate out. The solution, now containing tungsten compounds, undergoes pH adjustment causing yellow tungsten trioxide powder to crystallize. This powder undergoes hydrogen reduction, the crucial transformation. Inside tube furnaces heated to 1,800 degrees, hydrogen gas flows over tungsten trioxide. The hydrogen strips oxygen atoms, leaving metallic tungsten powder. But here's the challenge. Pure tungsten powder is useless. The particles don't bond. Press them together and they crumble. Tungsten's ultra-high melting point makes conventional melting impossible. No crucible survives temperatures required. The solution? Powder metallurgy. Powder metallurgy bypasses melting through sintering. Particles fuse below melting point under pressure and heat. Tungsten powder gets pressed into desired shapes using hydraulic presses, generating 50,000 psi. The compacts, called green bodies, are fragile, handle roughly, and they disintegrate. The green bodies enter sintering furnaces operating at 4,500 degrees in hydrogen atmosphere. At these temperatures, tungsten atoms migrate across particle surfaces, welding together without liquefying. The process takes 12 hours. What emerges has transformed. The powder compact becomes solid metal with 99% density. Dimensional changes are predictable but significant. Parts shrink 18% during sintering. Engineers must design oversized greens compensating for this shrinkage. Pure tungsten remains problematic. It's brittle at room temperature, difficult to machine. The solution? Alloying. Adding 2% thorium or lanthanum dramatically improves workability. These elements prevent grain growth during sintering, creating fine-grained structure that machines more easily. The most common tungsten product worldwide is tungsten carbide, tungsten powder mixed with carbon, sintered together. Tungsten carbide achieves hardness second only to diamond. Cutting tools made from tungsten carbide last 10 times longer than steel equivalents. Mining drill bits, machining inserts, industrial dies. Anywhere extreme wear occurs, tungsten carbide dominates. The material cuts steel like butter but shatters under impact. Drop tungsten carbide block on concrete and it explodes into fragments. The combination of extreme hardness and extreme brittleness defines tungsten's paradox. Wire drawing demonstrates tungsten's remarkable properties. The sintered tungsten gets heated to 3,000 degrees and drawn through progressively smaller diamond dies. The wire diameter reduces from 1/4 inch to thousandths of an inch, thinner than human hair for light bulb filaments. This drawing process work hardens tungsten, increasing strength. Modern LED lights made tungsten obsolete for household illumination, but specialty applications remain. Electron microscopes, X-ray tubes, high-temperature furnace elements. Anywhere electricity must flow through extreme heat, tungsten wire delivers. The element's resistance increases with temperature, making it self-regulating. In light bulbs, hot filament resists current flow, limiting power draw and preventing burnout from voltage spikes. That wire glowing white-hot at 6,000 degrees, tungsten operating at 70% of its melting point, yet lasting thousands of hours. Military applications drive demand relentlessly. Tungsten's density, 19.3 grams per cubic centimeter, nearly identical to gold, makes it ideal for kinetic penetrators. Armor-piercing ammunition uses tungsten or tungsten alloy cores. Fired from tank cannons at 5,000 feet per second, these projectiles punch through steel armor through sheer mass and velocity, not explosive force. The ethical controversy is intense. Depleted uranium performs similarly but raises radioactivity concerns. Tungsten offers equivalent performance without radiation, but mining's environmental cost is staggering. Each ton of tungsten requires processing 200 tons of ore, generating mountains of toxic waste. The metal that survives Earth's most extreme conditions is extracted through processes poisoning the planet. Swedish chemist Carl Scheele identified tungsten oxide in 1781, studying the mineral scheelite. Spanish brothers Juan and Fausto El Huyar isolated metallic tungsten 2 years later. The name derives from Swedish tungsten, heavy stone. For a century, tungsten remained laboratory curiosity. Everything changed when Thomas Edison needed light bulb filaments in 1879. He initially used carbon, which burned out quickly. By 1904, manufacturers switched to tungsten, revolutionizing electric lighting. World War I revealed tungsten's military value. High-speed steel cutting tools containing tungsten enabled mass production of weapons. Today's annual production exceeds 90,000 tons, with China dominating supply chains so completely that Western nations consider tungsten a strategic vulnerability. Carbon emissions remain problematic as tungsten production generates 8 tons of CO2 per ton of metal, primarily from energy-intensive processing. Recycling exists but remains limited. Only 30% of tungsten gets recycled, far below rates for aluminum or steel. Here's the secret we promised. Tungsten's incredible strength comes from its weakness. Pure tungsten is brittle, shattering easily. But that brittleness stems from its crystal structure. Atoms packed so tightly that dislocation movement, the mechanism allowing metals to deform, essentially stops. This atomic rigidity creates the highest melting point, extreme hardness, and resistance to deformation. The metal survives temperatures melting steel because its atoms simply refuse to move. Adding trace elements creates enough flexibility for workability while maintaining strength. From Chinese mountains to cutting edges worldwide, the transformation completes. We've mastered metal that defies conventional metallurgy, processing it through techniques developed when melting proved impossible. That drill bit cutting through rock, that filament glowing white-hot, that bullet-piercing armor, all share tungsten's fundamental contradiction. The strongest metal is also the most fragile. The element that won't melt is useless without powder metallurgy. We've learned to work with nature's extremes by accepting, not fighting, inherent limitations. Tungsten doesn't compromise. Neither do the engineers who've learned to shape it.
The metal that protects all other metals from rust. Picture this: 70% of the world's steel is covered with a thin layer of zinc. Bridges, skyscrapers, cars, ships, everywhere zinc stands guard, taking the hit from corrosion. Every second, the world produces 1.5 tons of zinc, 14 million tons per year. It's the fourth largest metal by production volume on the planet, after iron, aluminum, and copper. But they extract it unusually. Zinc is vaporized at 1,800 degrees Fahrenheit, and the vapor is collected. Yes, the metal turns into gas. How do they turn gray ore, mined a mile underground, into a bluish-silver metal that sacrifices itself for others? You'll learn why the ore burns in furnaces, how they collect metallic vapor, and why without zinc, the entire infrastructure of the planet would collapse. Watch to the end. The finale will show what's behind every galvanized beam. This is the story of the bodyguard metal that took on the corrosion of the entire world.
A mile underground, darkness, explosion, tons of rock crash down. This is a zinc mine, one of hundreds around the world where ore for the guardian metal is extracted every day. Underground dump trucks with 50-ton capacity haul ore to the mine shaft. An elevator the size of a house lifts the rock to the surface. The ore is dark, almost black. This is sphalerite, zinc sulfide. Crystals with diamond-like brilliance, but the metal content is only 10 to 15%. The rest is waste rock. Trucks carry the ore to the processing plant. The transformation from stone to metal begins. Massive cone crushers as tall as a 3-story building grind ore chunks the size of cars. The noise is deafening. The rock is crushed into gravel the size of fists. Then the gravel goes into ball mills, rotating steel drums 16 feet in diameter, filled with steel balls the size of watermelons. The drum rotates, balls fall, grinding the ore into fine powder. After 8 hours of grinding, you get gray dust, particles the size of sand grains. The ore powder is mixed with water, creating gray liquid slurry called pulp. It's pumped into huge flotation machines, tanks with volumes of 3,500 cubic feet. Chemical reagents are added, foaming agents and collectors. Mixers are turned on and air is fed from below. The magic of flotation begins. Millions of air bubbles rise through the pulp. Particles of sphalerite, zinc ore, stick to the bubbles and float up. A gray foam forms on the surface, 20 inches thick. This foam contains zinc. Waste rock settles to the bottom and is drained off. The foam is collected, filtered, dried. The result is concentrate, powder containing 50 to 60% zinc. From 100 tons of ore, you get 10 to 15 tons of concentrate. This concentrate is loaded into rail cars and shipped to the smelting plant. There begins the real alchemy, turning powder into molten metal. And this is a process where metal turns into vapor. At the plant, concentrate is loaded into fluid bed roasters, massive steel cylinders 66 feet tall. Hot air under pressure is blown in from below. The concentrate powder lifts up, floating in the air like dust. Gas burners are ignited. Temperature rises to 1,650 degrees Fahrenheit. The zinc sulfide ignites. Yes, the ore burns. Sulfur oxidizes, releasing enormous amounts of heat. Sulfur gas flies up the stacks. It will be captured and turned into sulfuric acid. And zinc sulfide transforms into zinc oxide, a gray-white powder. The temperature in the furnace is so high that the walls glow red. The roasted concentrate, zinc oxide, is cooled and mixed with coke, crushed coal. The proportion, 3 parts oxide to 1 part coke.
This mixture is loaded into vertical retort furnaces, steel towers 50 feet tall, lined inside with refractory silicon carbide. Heating begins. Temperature starts climbing. 1,800 degrees, 2,000 degrees, 2,200 degrees. At 2,200 degrees Fahrenheit, carbon begins taking oxygen away from zinc oxide. A reduction reaction occurs. But something amazing happens. Zinc doesn't melt. Its boiling point is only 1,665 degrees, but the furnace is at 2,200. So zinc immediately turns into vapor, metallic vapor. Inside the furnace, atoms of gaseous zinc are flying around. The vapors rise up and exit the furnace through piping. They enter a condenser, a special cooled chamber. Temperature in the condenser is around 840 degrees, below boiling point but above melting point of zinc. The vapors condense. Drops of molten zinc settle on the condenser walls, glowing orange. Liquid metal flows down the walls and collects in a receiver. This is crude zinc, contains impurities of lead, cadmium, iron. Purity around 98%. Each furnace produces up to 100 tons of zinc per day. The metal is cast into molds. The result is ingold bars weighing 55 pounds each, silver gray with a bluish tint. For some applications, pure zinc is needed. Then it's refined, purified by distillation. Crude zinc is heated to boiling in a vacuum furnace. Under reduced pressure, boiling point drops to 1,300 degrees. Zinc vaporizes while impurities remain solid. Zinc vapors are condensed in a cooler. The result is refined zinc with 99.99% purity. This zinc is cast into ingots. On the ingot surfaces, a characteristic pattern forms, crystalline designs resembling frost flowers on glass. This is called zinc flowers. Ingots are stacked. Zinc is ready for use, but its main application awaits in hot dip galvanizing baths. There, steel products will receive corrosion protection. The process looks impressive, like baptism of metal by fire. A steel beam 40 feet long is immersed in a bath of molten zinc. Temperature 840 degrees. The beam completely disappears in the silvery liquid. Chemical reaction begins instantly. Zinc reacts with iron on the steel surface, forming a layer of intermetallic compounds, a solid alloy of zinc and iron. This layer bonds permanently to the steel. On top, a layer of pure liquid zinc. The beam is held in the bath for 1 to 2 minutes. Then it's pulled out. Excess molten zinc drains back. In air, the coating quickly solidifies. The surface becomes silvery, matte, with the characteristic pattern of crystals, zinc flowers. Coating thickness from 2 to 8 thousandths of an inch. That's just fractions of an inch, but it's enough. The galvanized beam won't rust for 50 to 70 years. Even scratches aren't scary. Zinc continues protecting. It's about electrochemistry. Zinc is more active than iron. When corrosion begins, zinc oxidizes, not steel. Zinc sacrifices itself, protecting iron. This is called cathodic protection. World production of galvanized steel, 55 million tons annually. This uses 6 million tons of zinc. Without zinc, modern cities would be impossible. 70% of zinc goes to protecting steel. But there are other applications. Brass, an alloy of copper and zinc, has been known for thousands of years. Contains 15 to 45% zinc. Golden, strong, easily worked. Brass is used for plumbing fixtures, musical instruments, cartridge cases, decorative items. Zinc die casting, a method for manufacturing complex parts for automotives and electronics. Molten zinc is injected under pressure into steel molds. The result is complex-shaped parts accurate to tenths of thousands of an inch. Zinc batteries, still used by the billions. Zinc powder in chemical industry. Zinc oxide in rubber industry, cosmetics, medicine. Zinc ointment heals wounds. World zinc mining, 14 million tons per year. China produces 40%, 5.5 million tons. Peru, Australia, USA, India, other major producers. Zinc price, around $3,000 per ton.
The history of zinc as a separate metal began late. Europeans knew brass since ancient Rome, but couldn't obtain pure zinc. The problem, zinc evaporates when heated. Indian and Chinese metallurgists in the 16th century learned to condense zinc vapors in closed retorts. In Europe, pure zinc was obtained by German chemist Andreas Markgraf in 1746. But mass production began in the 19th century. Revolution happened in 1836 when French engineer Stanislas Sorel discovered the hot galvanizing process. He found that immersing steel in molten zinc protects from corrosion. This changed construction forever. Before galvanizing, steel structures rusted within years. With galvanizing, they serve for decades. The Eiffel Tower is painted, but many bridges from that era are galvanized and still standing. Today, without galvanized steel, skyscrapers, bridges, power lines, ships are impossible. Zinc, the invisible guardian of infrastructure.
And so, having traveled from explosions a mile deep through giant crushers and flotation tanks, through fluid bed furnaces at 1,650 degrees and retort towers at 2,200, through transformation into metallic vapor and condensation, zinc emerges, the bodyguard metal of modern civilization. The silvery metal that sacrifices itself, protecting steel from rust. The fourth largest metal by production on the planet, without which all infrastructure would collapse. Every time you see a steel bridge beam, a roofing sheet, or a car body, know they're protected by a thin layer of zinc as thick as a human hair. A layer that takes on corrosion, oxidizes instead of steel, slowly destroys itself, saving the structure. This is a story of nobility at the atomic level, how one metal protects another, sacrificing itself. From underground explosions to silvery skyscraper beams, zinc's journey spans several weeks and 2,200 degrees. The metal that vaporizes to protect, that oxidizes so others don't rust. The invisible shield of 14 million tons annually, standing between steel and corrosion. Zinc. This is why bridges don't collapse, roofs don't leak, and cars don't turn to dust in 5 years. The guardian metal, the sacrificial metal, the metal without which the modern world would simply fall apart from rust.
Every second, jet engines spinning at 12,000 revolutions per minute thrust hundreds of passengers across continents. But here's what defies physics. Inside those engines, turbine blades made of nickel alloy operate at 3,000 degrees Fahrenheit, temperatures exceeding their own melting point by 200 degrees. Picture holding ice cubes in boiling water without them melting. That's the metallurgical miracle happening 35,000 feet above your head. How does metal survive temperatures that should liquefy it? How do engineers grow crystals larger than your hand from molten metal? Stick around till the end, you'll discover the jaw-dropping secret of single crystal manufacturing that eliminated metal's greatest weakness, and why a single turbine blade costs more than your car, yet lasts 20 years in literal hell. The story begins in specialized foundries where clean room standards rival semiconductor fabs. These facilities maintain air purity of less than 100 particles per cubic foot, 10,000 times cleaner than normal atmosphere. Even microscopic dust particles cause catastrophic flaws in turbine blades spinning at speeds where centrifugal forces generate stresses exceeding 70,000 pounds per square inch. That's pressure crushing steel like aluminum foil. Workers suit up in full-body cleanroom gear before entering casting halls. Inside, massive vacuum furnaces standing 2 stories tall and weighing 80 tons create environments replicating outer space. Vacuum pumps evacuate air until pressure drops to 1/1,000,000th of atmospheric pressure. At these conditions, materials behave differently. Impurities vaporize instantly. Gases trapped in metal escape, leaving behind purity impossible at normal pressure. Processing single batches costs $50,000 in electricity alone. Next comes mold preparation, where ceramic shells, think pottery on steroids, get built layer by microscopic layer. Technicians dip wax patterns shaped like turbine blades into ceramic slurry 10 times, waiting hours between coats. Each layer adds thickness thinner than human hair. After 20 days of coating and drying, workers melt wax away in autoclaves, leaving hollow ceramic molds with internal channels more complex than human circulatory systems. These molds contain passages narrower than spaghetti strands, designed to cool blades from inside during operation. Some channels measure just 0.08 of an inch across, thinner than credit cards. Manufacturing these passages requires such precision that lasers verify every dimension. One blocked cooling hole means blade failure at 300 degrees lower temperature. That's difference between safe flight and catastrophic engine disintegration at cruise altitude, scattering turbine fragments through fuselage like shrapnel.
Giant crucibles containing nickel-based superalloy, mixtures of nickel, chromium, cobalt, aluminum, titanium, plus 6 other elements in exact proportions. Heat to 2,700 degrees Fahrenheit. Picture liquid metal glowing white like miniature stars captured in ceramic containers. This superalloy, developed through decades of research, contains more expensive elements per pound than fine jewelry. A single turbine blade uses materials costing $800 before any manufacturing begins. Robotic arms lower ceramic molds into this molten inferno with precision measured in thousandths of inches. Timing matters critically here. Pour too fast, turbulence creates defects. Too slow, metal solidifies prematurely. Furnaces tilt at exactly 2 degrees per second, filling mold cavities in 17 seconds. During this pour, metal temperature drops 300 degrees, requiring computer-controlled heating to maintain consistency. One temperature fluctuation of 5 degrees ruins the casting, wasting months of preparation.
Now comes the magic, directional solidification. The filled mold sits atop a water-cooled chill plate at 70 degrees Fahrenheit while surrounded by heating elements maintaining 2,400 degrees above. This creates the steepest temperature gradient in metallurgy, over 2,000 degrees difference across 6 inches. That's transitioning from Arctic to volcanic conditions in the space between your thumb and pinky. Slowly, incredibly slowly, a computer-controlled mechanism lowers the mold through the furnace at speeds of 6 inches per hour. Picture watching paint dry, then slowing that down tenfold. As the mold descends, metal solidifies from bottom upward in a razor-thin freezing front. This directional cooling forces crystal growth in one direction only, upward, eliminating horizontal grain boundaries where cracks normally form. The process takes 14 hours for a 4-inch blade. Rush it by even 10% and polycrystalline grains form, destroying blade strength. But here's where physics becomes art. At the mold bottom sits a grain selector, a corkscrew-shaped passage so narrow only one crystal nucleus fits through. As metal solidifies upward, countless tiny crystals form at the chill plate. They compete, growing upward like metallic trees racing toward sunlight. Most hit the spiral walls and stop. Only the perfectly aligned crystal, the one matching the spiral's orientation, passes through this metallurgical gauntlet.
This step is critical because it ensures the entire blade, every atom from root to tip, belongs to one continuous crystal lattice. No grain boundaries exist anywhere. Normal metals contain millions of grain boundaries per cubic inch. Single crystal blades contain 0. Without boundaries, there are no weak spots where atoms slip past each other under stress. The crystal structure extends uninterrupted through the entire blade like a three-dimensional molecular Kevlar vest, with atoms locked in perfect geometric formation. After solidification, blades undergo solution heat treatment at 2,200 degrees Fahrenheit for 2 hours, then quench in inert gas. This locks crystal structure permanently and precipitates microscopic strengthening phases throughout the lattice. Next comes aging heat treatment, multiple cycles at precisely controlled temperatures that cause nanoscale particles to form. These particles, called gamma-prime precipitates, occupy 70% of the alloy's volume. Picture this. Imagine a three-dimensional checkerboard where hard particles pin the crystal lattice, preventing atoms from sliding. These precipitates remain stable at temperatures where other metals liquefy. They're the secret allowing nickel alloys to maintain strength at 3,000 degrees, temperatures where aluminum vaporizes, titanium melts, and even steel becomes taffy. The heat treatment process takes 96 hours of precise temperature control. Deviate by 15 degrees at any point and mechanical properties drop 40%.
Coating application transforms already sophisticated blades into thermal protection systems. First, a metallic bond coat, aluminum-rich alloy, gets applied via high-velocity plasma spray at 20,000 degrees Fahrenheit. Metal particles accelerate to twice the speed of sound, impacting the blade surface with such force they cold weld instantly. This creates a rough surface for subsequent layers while providing oxidation resistance. Then comes the thermal barrier coating, yttria-stabilized zirconia ceramic applied atom layer by atom layer using electron beam physical vapor deposition. In vacuum chambers, electron beams vaporize ceramic ingots. The vapor condenses on rotating blades, building up a coating 0.08 of an inch thick with a columnar microstructure full of microscopic pores. These pores act like thermal insulation, trapping air pockets that reduce heat transfer. The ceramic coating lowers blade temperature by 400 degrees, the difference between survival and meltdown. Modern engines couldn't exist without this coating technology.
This wasn't always possible. Back in 1940, early jet engines used cast iron turbine blades lasting 20 hours before failure. Temperatures barely reached 1,400 degrees Fahrenheit. The breakthrough came when Pratt & Whitney researcher Frederick Vierling invented directional solidification in 1966, eliminating transverse grain boundaries and doubling blade life overnight. The true revolution arrived in 1982 when General Electric and Pratt & Whitney independently perfected single crystal casting. Turbine inlet temperatures jumped from 2,000 degrees to 3,000 degrees Fahrenheit, a 50% increase enabling massive efficiency gains. Modern turbofan engines achieve fuel efficiency triple that of 1960s designs. Today, advanced engines like the GE9X powering Boeing 777X aircraft operate at 3,200 degrees, with pressure ratios reaching 60:1. These engineering advances cut aviation fuel consumption by 65% per passenger mile over 50 years.
Carbon emissions drop by 12% when replacing older turbine blades with modern single crystal versions in existing engines, equivalent to removing 18 million cars annually from global fleets. Airlines save over $47 billion yearly through improved fuel efficiency. Maintenance costs drop 58% because single crystal blades last 3 times longer than conventional ones. So here's the secret promised. These blades don't actually survive above their melting point through material strength alone. They're actively cooled by air bled from the compressor, flowing through those microscopic internal channels at supersonic speeds.
This cooling air, already compressed to 400 degrees Fahrenheit, seems hot by human standards, but runs ice cold compared to the 3,000-degree combustion gases outside. Combined with ceramic coatings reflecting heat like mirrors, the actual metal temperature stays below 2,000 degrees, hot enough to glow orange, but survivable. From molten metal to flying miracles, cycle completes. Single crystal turbine blades represent humanity's most sophisticated metal casting achievement. Objects where every atom's position matters, where crystal orientation determines survival, where manufacturing tolerances make computer chips look crude. We've engineered metal to survive in conditions nature never intended, creating materials that work at their physical limits. That's not just manufacturing, that's molecular architecture enabling the modern world's ability to shrink distance itself.
Every year, humanity extracts over 2 billion tons of iron ore from Earth's crust. Picture this. More than half of our planet's entire weight is iron, most locked in the core, creating the magnetic field protecting all life. But here's what shocks engineers worldwide. We're standing on the most abundant metal in the universe, yet accessing it requires temperatures hotter than volcanic lava. How does rust-colored rock transform into gleaming steel skyscrapers? How do ancient mountains become modern civilization? Stick around till the end. You'll discover why iron shaped human history more than gold ever did, and the jaw-dropping secret hiding inside every bridge, car, and building around you right now. The story begins in Western Australia's Pilbara region, where iron mountains stretch across landscapes older than dinosaurs. Massive excavators, standing 8 stories tall, picture buildings that walk, tear into rust-red cliffs with bucket teeth weighing 12 tons each. These mechanical giants rip through rock layers formed 3 billion years ago when Earth's oceans first rusted. With thunderous crashes echoing across 40-mile-wide craters, each excavator loads haul trucks carrying 400 tons per trip. That's the weight of 80 elephants moving at 40 miles per hour on tires taller than basketball hoops. Processing 30 million tons annually from single mines, enough iron ore to build 12 Golden Gate bridges every single day. Next comes crushing, where house-sized jaw crushers, imagine dinosaur mouths made of hardened steel, pulverize boulders into gravel-sized chunks. With deafening roars splitting eardrums even through protection, these crushers generate forces exceeding 20,000 pounds per square inch. Clouds of red dust billowing upward create artificial sunsets visible from space satellites. Conveyor belts stretching 12 miles long, longer than Manhattan, transport crushed ore at 18 miles per hour. Workers riding inspection carts traverse distances requiring 25 minutes one way. That's enough belt to wrap around 300 football fields. Every hour, 50,000 tons flow through this system, weight equivalent to 5 Eiffel Towers moving continuously past checkpoints. Giant grinding mills, standing 5 stories tall, with diameters matching Olympic swimming pool widths, pulverize rock into fine powder. Inside these rotating drums, 20-ton steel balls, each weighing more than shipping containers, tumble with ore, creating grinding thunder heard miles away. Operators monitor vibrations. Wrong frequencies mean catastrophic bearing failures, costing millions. At rotation speeds creating gravitational forces triple normal Earth gravity, particles shrink to powder finer than talcum. Processing 8,000 tons hourly, that's filling semi-truck after semi-truck every 30 seconds. This powder, called concentrate, contains 65% iron. Magnetic separators then extract iron particles using forces strong enough to levitate railroad spikes, leaving waste rock behind. Next comes the blast furnace, a towering inferno standing 30 stories high, its steel shell glowing dull orange even from outside. At internal temperatures exceeding 3,000 degrees Fahrenheit, hot enough to vaporize aluminum instantly, iron ore transforms into liquid metal. Picture Dante's Inferno engineered with precision. Measured charges of iron ore, coke, and limestone descend from the top, while superheated air blasts upward at 2,000 degrees from ring-shaped nozzles called tuyeres. This creates a raging chemical storm, where carbon monoxide rips oxygen from iron oxide molecules. The reaction releases enough heat to melt granite. Every 3 minutes, sensors check 20 different parameters. Without precision, furnaces explode with force demolishing city blocks. The blast furnace operates continuously for 15 years, never cooling, never stopping, like Earth's core relocated to industrial facilities. Inside this chemical reactor, materials descend through distinct zones. Upper regions preheat incoming ore. Middle zones drive off moisture and carbon dioxide. Lower depths become hell itself, where iron liquefies. At the hearth bottom, molten iron collects at 2,800 degrees Fahrenheit, dense as lead but flowing like water. Every 4 hours, workers drill through clay-plugged tap holes. Liquid iron erupts in blinding white rivers, flowing through ceramic channels into railroad cars holding 300 tons each. This step is critical because timing determines metal purity. Tap too early, slag contaminates. Too late, furnace pressure ruptures containment walls. After tapping, slag, lighter impurities floating atop molten iron, gets diverted into separate channels. This glowing amber liquid, essentially liquefied rock, contains calcium, silicon, and aluminum oxides stripped from ore. Rather than waste, it becomes roadbed material and cement ingredient recycled at 98% rates globally. The molten iron, called pig iron, contains 4% carbon, too brittle for construction. Picture glass that looks metallic. Drop pig iron from waist height, it shatters into fragments. Next comes the basic oxygen furnace, where pure oxygen blasted at supersonic speeds through 3-foot diameter lances burns away excess carbon in 17 minutes. Flames shooting 70 feet high, temperatures hitting 3,200 degrees, create hurricane-force winds inside steel vessels holding 350 tons of liquid metal. Steelmaking requires precision rivaling brain surgery. Computer-controlled oxygen flow adjusts by milliseconds. Operators add exact amounts of manganese, silicon, chromium, elements changing steel properties dramatically. Too much carbon, steel cracks in winter cold. Too little, metal bends under load. Picture this: alloying elements get injected via submerged lances. Electromagnetic stirring, invisible but powerful, homogenizes composition. Samples extracted every 3 minutes get analyzed via spectrometers, determining chemistry within seconds. Modern furnaces achieve carbon content accuracy to 0.01%, difference between skyscraper standing or collapsing. After refining, liquid steel flows into continuous casting machines producing slabs 30 feet long, weighing 25 tons at rates of 1 slab every 90 seconds. This wasn't always so advanced. Back in ancient Anatolia around 1300 BC, Hittite metallurgists discovered heating iron ore with charcoal produced workable metal. That breakthrough, accidental furnace conditions reaching iron's melting point, changed human civilization forever. Iron tools outperformed bronze, enabling agriculture revolution. The breakthrough came when British inventor Henry Bessemer patented his converter in 1856, slashing steel production time from 24 hours to 17 minutes. Suddenly, steel costs dropped 90%. This single invention built modern cities. Skyscrapers, bridges, railroads exploded across continents. Today, global steel production exceeds 1.9 billion tons annually. That's enough to build 75,000 Eiffel Towers yearly, or manufacture 43 million automobiles, or construct bridges connecting every coastline on Earth. Carbon emissions drop by 62% when using recycled steel versus virgin ore, equivalent to removing 12 million cars annually. Industry saves over $80 billion yearly through scrap recycling. Processing costs drop 43% because melting scrap requires 1/3 the energy of blast furnaces. So here's the secret promised: Every ton of steel you see, bridges, buildings, cars, will be recycled indefinitely. Unlike plastic decomposing into microparticles or paper pulping into mush, steel never degrades. Magnetic separation extracts it perfectly from demolished structures. That girder in your office building might contain steel from 1930s locomotives. Your car's frame could include battleship armor from World War II. Nothing disappears. Metal merely transforms, reborn eternally. From ancient mountains to modern marvels, cycle completes. Iron, humanity's most essential metal, circulates through civilization like blood through veins. We're not consuming Earth's iron, we're borrowing it, briefly, before passing it forward to futures we'll never see.
Every year, the world melts over 1 billion tons of pig iron. But where does all that fiery metal come from? Imagine a giant furnace as tall as a 35-story skyscraper that never sleeps. Its guts glow like the Earth's core, and the temperature hits 3,600 degrees Fahrenheit. That's 2,000 Celsius. This is a blast furnace. They don't just melt metal here. They give birth to the heart of industry. But there's a secret that only the guys standing at the tap hole know. If you stick around to the end, you'll find out what's really happening in the center of this burning fortress, and why it changes everything. Imagine a colossal tower, taller than a 35-story skyscraper. The ground beneath your feet vibrates slightly from its relentless work, and the air is filled with a hum, like the breathing of a giant beast. At night, its top glows, pushing back the darkness. This is a blast furnace, a massive vertical smelter where 24 hours a day, 7 days a week, the magic of turning ore into metal happens non-stop. Why blast furnace? The name comes from the process itself, and it's no accident. The whole secret to a blast furnace is the constant blast of incredibly hot air that fuels the fire and kicks off all the necessary reactions. If you were to slice a blast furnace open, you'd see it looks like a stretched out bottle. Every part of it has a name and a purpose. The walls of the furnace are lined with special refractory bricks, capable of withstanding temperatures that would melt solid rock. This is a true fortress, built to tame fire itself. So what do they feed into this fiery throat? The process is like cooking from a very strict recipe. The mix of ingredients loaded into the furnace is called the charge. Here are its main components: iron ore, fuel, coke, and fluxes. These three ingredients are loaded into the furnace in precisely measured layers. A layer of coke, then a layer of ore with fluxes, then coke again, and so on. Every few minutes, a new batch weighing tens of tons is sent into the furnace. The iron ore is the foundation of it all. They usually don't just use raw ore dug from the ground, but specially prepared sinter or pellets. These are baked clumps of fine ore, or rolled balls of ore concentrate. The main goal is to have as much iron oxide in the raw material as possible, from which the oxygen will later be ripped out. Coke is coal that's been cooked in special ovens without access to air. After this treatment, it becomes strong, porous, and burns with an immense amount of heat. But that's not its only role. The carbon that makes up coke is the real magician that turns ore into metal. The flux is most often ordinary limestone. Why is it needed? The ore and coke always have useless impurities, so-called gangue. The limestone helps to bind these impurities, forming an easily meltable slag. So, the charge is loaded. What's next? This is where it gets interesting. Two streams move towards each other. From the top, the layers of the charge slowly descend, and from the bottom, a hurricane of superheated gases rushes up to meet them. It all starts at the bottom, in the hearth. Through special pipes called tuyeres, air heated to a scorching 2,200 degrees. Fahrenheit, 1 to 200 Celsius, is blasted into the furnace under huge pressure. That's hotter than volcanic lava. Meeting the red-hot coke, the oxygen in the air instantly ignites. The temperature in this zone skyrockets to 3,600 degrees Fahrenheit, 2,000 Celsius. This creates carbon dioxide. But as it rises higher and passes through new layers of coke, it turns into another gas, carbon monoxide. And this gas is the real oxygen thief. As this searing hot stream of gas rises up the furnace shaft, it envelops the chunks of ore and begins to greedily rip the oxygen from them, leaving behind reduced, spongy iron. The reduced iron continues its journey downward into hotter and hotter zones. It passes through the glowing layers of coke and, like a sponge, begins to soak up its carbon. And here's where something amazing happens. Pure iron melts at a very high temperature of 2,800 1,530 nanometers. But soaking up carbon dramatically lowers that melting point. That's why a blast furnace doesn't produce pure iron, but an alloy of iron and carbon, pig iron, which becomes liquid at just 2,200 nanometers, 1/200 nanometers. Roughly every 40 to 60 minutes, enough liquid products have collected in the bottom of the furnace. It's time for the climax, a truly mesmerizing sight. A furnace worker, the keeper, uses a special drill to punch open a hole in the furnace wall, the tap hole. First, they tap the slag. It's lighter than the iron, so it floats on top. It's a molten, lava-like mass that flows into special ladles. And then they open the iron tap hole, and a dazzling, sparking stream of molten metal erupts with a roar. This is the River of Fire. The temperature of this stream is around 2,700 degrees Fahrenheit, 1,500 Celsius. It flows down special troughs, bathing everything around in a blinding light, and fills giant ladles that look like railway tankers. Each of these ladles holds hundreds of tons of liquid metal. From here, the pig iron will be sent to its next stage, either poured into molds or, more often, sent for further processing into steel. A blast furnace is an amazing operation that produces more than just pig iron. The byproducts are just as important. The blast furnace slag, which we've already mentioned, becomes a valuable raw material for making cement, building blocks, and road aggregate after it's cooled and crushed. The blast furnace gas that comes out of the furnace isn't just released into the atmosphere. It's cleaned of dust and used as fuel to heat the very same air that's blasted back into the furnace. It's a closed-loop system that makes the process more economical. Without a doubt, metallurgy is a serious challenge for the environment. However, modern technologies are constantly evolving. When blast furnaces are modernized, powerful filters and cleaning systems are installed to capture dust and harmful gases. Scientists and engineers around the world are working on creating green technologies, like using hydrogen instead of coke, to make metal production cleaner. But for now, the blast furnace remains the king of metallurgy. And every time you see a bridge, a skyscraper, or a train, remember these fiery giants and the people who tame rivers of fire to give the world a strong and reliable foundation. For 75 years, from the late 19th century to the 1970s, the USA was the undisputed world leader in the production of pig iron, steel, and rolled products. During this period, the American iron and steel industry wasn't just a sector of the economy, it was the key or barometer of the American economy. In the 1920s, for example, the country produced about half of the world's pig iron. Imagine that. Every other ton of this strategic metal in the world was born right here in American furnaces.